Hi there, nice little lesson for us here today, carrying on with our work last time on transformations of 2D shapes using matrices. And you'll notice the little clever graphic I've got here, which I've nicked off the internet. I didn't think of it. This is actually a rotation. You get taught about rotations as well. I don't think we saw any last time, other than I think we saw that the rotation either 90 degrees one way or 90 degrees the other way. Now this graphic implies actually there's more to rotations than meets the eye. I've got a specific one here that says cos 90, and you should know what cos 90 is. If you're not sure, type it in. You can actually tell by just looking at the graph. Actually, the graph does this. That's the cos graph, and 90 is there, so it's naught. Sine of 90, well again, sine of 90, you can tell by the graph. You can type it in if you prefer. Sine of 90 is there, and therefore that's 1. So minus sine of 90 must be minus 1, and we've got another cos of 90 there. So that is well, I'm suggesting to you it's a rotation by 90 degrees. I'm not quite sure yet which way. Let's make up a point. It says 2, 3. Of course, 2, 3 is 2 across, 3 up. So there. That's on my very dodgy scale. So let's work out where it goes. If I multiply out, that's 0, that's 3. Don't know why I've gone square brackets all of a sudden. Makes no difference. That's minus 2 if I do that. So if I draw that, it's 3 across, 2 down. You can see that is definitely a rotation. Well, it seems to me to be a rotation anyway, by 90 degrees, but that's clockwise. So here we have a suggestion that 90 degrees clockwise can be gained using this, and it also suggests to me that if you do cos of alpha, for instance, sine of alpha, minus sine of alpha, cos of alpha, and you allow yourself to have any alpha, it will be a rotation clockwise by alpha degrees. So all of a sudden this is an extension. And yet actually if you look at this picture, this is why the graphic's so clever. A1, A2, it has been rotated. It's now A1, A2, but it's been rotated 90 degrees. So a little starter for you. You're meant to know some of these. I did say this last time. Look back at your notes. I want you to look up what these were. This was an old exam question. Admittedly, it was a fair few years ago, shall we say. But in June 2008, the students were asked what these were. And these kind of questions come up quite a lot. They're expected to know and to be able to describe properly what these are. So pause the video, write your answers down, and then come back to us. Okay, so these are the answers. First one is an enlargement. Whenever you get these naught noughts and these numbers are both the same, it's an enlargement. Scale factor 6. This is a reflection, and the line y equals 6. This is a stretch, and again it's like the first one actually, but they're different numbers, so only one of them is stretch. It's a one-way enlargement, if you like, a stretch. And this last one is rotation, and you might have got that because it says it's a rotation clockwise. Notice if I do cos of 36.9 and sine of 36.9, I think that would work. So I'm just going to do it on my calculator now. Make sure you're in degrees. So I'm just checking my calculator. No, mine wasn't, so good job I checked. But I'm just going to now do cos of 36.9 degrees. And give or take a bit, it's 0.8. So you can see that as well. This is the one we were looking at just now. And this is minus sine of 36.9 and cos of 36.9. So it kind of highlights that what we saw at the beginning is coming up again. This is becoming more and more important. We're meant to know these funny rotations. Who would have thought it's a rotation by 36.9 degrees? And there it is. So this is another table showing us all the different transformations we're meant to know with their associated matrices. You'll notice there's a couple at the bottom I don't think we've seen so far. They're called shears, and I want to explain what they are during this lesson. But I also want you just to look at the determinants again. So when the determinant is 1, remember the area stays the same. Well, that's fair enough, but it's a rotation. Now, there's a couple of other things which give you a determinant of 1. So having a determinant 1 doesn't make it a rotation, but it makes it more likely, perhaps. Perhaps that's the best way to think about it. But -1 does seem to be a reflection. To get a negative, you've got to have reflected it. And then you get these stretches determined by these funny missing numbers. And an enlargement where it's k is k squared. So just look out for these. We're meant to know these things. Anyway, so rotation. Find the image of this. So I did suggest to you that just now these rotations have a funny formula, and there it is. That's the formula. Now notice this is anti-clockwise. The one we saw was a clockwise one, and therefore the cos was still in the same place, but the minus on the sine went down to there. So you might want to write them both down. Just bear that in mind. Cos is always on that diagonal, sine's on that. And anti-clockwise, the one that they've told us about is that minus up there. So anyway, this says find the image of the point 4, -2 after a 75-degree rotation anti-clockwise. So this is cos 75 minus sine 75 based on what we just said. Sine 75 there and cos 75 there again. And we do that to 4, -2. And type it into your calculator. You're going to get an answer from that, and it won't be very pretty because it's to 2 decimal places. Make sure you say you're in degrees. Other than that, that's what I got when I did it. So not very pretty, but fine. If that's if that's what you got to do, that's what you got to do. More often than not, you get nicer degrees than 75. You might get 60 degrees or 30 degrees or 45 degrees. One of the special angles. In general, shears for an x-axis invariant. Now, basically, it means anything on the x-axis won't move. That's what invariant means. For shears, which are x-axis invariant, it means that points on the x-axis don't move. It means that points not on the x-axis move a distance that is proportional to how far away they are from the x-axis. Now, that might seem weird. In class, I'll try to show you what that means in terms of me standing on someone's foot and me pushing them away. It might sound weird, but I'll show you what I mean by that. But for now, I want you to think of this here. So I've drawn a fairly dodgy looking shape, and you'll notice 2 of the points are on the line, the x-axis. So those 2 points aren't going to move. They're going to stay exactly where they are when I do this, whatever it is to it. And I don't know what that is. Now, I suppose I could just do this. So these are the coordinates of my funny shape. You can always go back and check if you need to. This was the matrix I wanted to do it on. So if I multiply that out, you can quite easily see I get this. So type it into a calculator, you'll get this. GDC, by the way, it just stands for graphical display calculator. So posh calculators. Ones with you can draw graphs on. So now I've got that. You look at the original shape and you look at the new shape. And you think, ooh, what's happening there? Well, let's just look. Notice the 2 points on the line, these 2, stayed exactly where they were. They didn't move. They are invariant. That's what invariant means. Now, this one is 1 away. It is, sorry, from the x-axis. I'm going the wrong way now. It is 2 away. So it's 2 up. So because it is 2 up, it is going to move more than this point is. This point here is 1 up. So how far has this point moved? Well, it has moved 1, 2 away. So you can see it has gone 2. But this point here, because it was twice as far up, has moved 1, 2, 3, 4. It has moved 4 away from where it was originally. And notice it moves in the direction of the x-axis. But the movement, the size of that movement is determined by the distance away from the x-axis. And we call this a shear with x-axis invariant. And then you just basically pick any point. You can pick any point you like. So 0, 1 is not a bad one to pick. Where is that? 0, 1. Well, weirdly, it wasn't even on my graph. But 0, 1, I'm suggesting, goes to 2, 1. It's a strange choice, actually. Why did I pick that one? I'm just trying to see. I suppose the only thing I would say about it is the fact that because it's off the x-axis, you can see how it's going to move. If I picked any point down here, it wouldn't move, so it wouldn't tell me anything. And 0, 1, I'm really saying it's going to move. 0, 1 is going to move 2 places. So I'm highlighting the fact that it's effectively 1 square up. It makes it move 2 to the right. But you can pick, I could have picked there. I could have said, 2, 1. Pick that point. 2, 1 goes 2. And I could have said 4, 1 if I wanted to. But I chose this one instead. So, and that exercise for us, there's 3 questions I want you to have a look at prior to coming in to class. So I've said draw the unit square after the transformation. So draw the unit square and then basically transform it by this and then describe it. Tell me what happens to it. Secondly, I want you to draw the unit, the 2D shape shown here. Well, this one here. And I then want you to transform it by this matrix, and I want you to describe the transformation again. And finally, it's back to the unit square again. Remember, the unit square is just, it goes to 1, 1. It goes, that's the unit square. So in question 1 and 3, you're using the same one. And you're going to transform it by this. You're going to draw it, and then you're going to describe the transformation. So I'd suggest you pause the video. Once you pause the video, you'll be able to then try to do those 3 questions. And you can also always go and have a look at my answers and get your head around it if you're not sure what's going on. But certainly by the end of this, I want you to be able to do it. Okay, so pause the video and then see if you can do it. Okay, so these are the answers. You'll notice when I've done this multiplication, I've drawn this funny thing here. Look at that, that's gone all the way over there. But notice 2 points didn't move. So I think that is definitely a shear. They didn't move on the x-axis, so it's a shear with the x-axis invariant. And 0, 1, well, there was a 0, 1 on this picture. Where did 0, 1 go to? It went to there. It went to 3, 1. And you can see that. It won't always be that point there, but yeah, if you have got a point that you can show, it's easier to see. The second one then, I told you to draw this funny blue shape. And once I've drawn it, I got this shape. Now you might have been a little bit confused as to which way around to draw it. So I would have picked that point first, then that point, then that point, then that point. And then try to mirror that. And in any case then, what has happened to it? So it's definitely not a shear to the with x-axis invariant, because this point here, they've moved, they've gone up there, but it would seem. Or have they? Have a look what happened. Which point went where? I don't think it looks like it's a reflection, but I don't think it is. So this point here is 1 away, and that point has gone 2 up. It says 1, 0 went to 1, 2, and it did. That point went to there, and this point here is 1 away, so that also went 2 up. That's gone to there. So if you like, that's gone to there, and that's gone to there. This point here is 2 away from the y-axis. So this point went 1, 2, 3, 4 away. Notice it went twice as far. And this point, also 2 away, went 4. It's gone up to there. So it looks like a reflection, but it's not. It's a shear with y-axis invariant. And it's all to do with how far you are away from this y-axis. This y-axis. This last one then is also, it claims y-axis invariant. And you can see that more clearly here. Those 2 points haven't moved. That's the giveaway. This is 1 away, and it's gone 1, 2, 3. And that's why you can see it goes to 1,3. This is times by 3 for every 1 away it is. This one is also 1 away, so it goes 1, 2, 3. You can see it has worked. 1, 0 went to 1, 3. So that's the way you've got to write them in your answers. So there you go, exercise 3C. We'll do that in class, and obviously I'll try and explain that a bit better. And remind me to mention the standing on someone's feet experiment. So all the best.